Okay, this is going to be the first video on section 6.2, and we're going to be looking at some properties of power series. We have a major theorem here that says it has three parts for combining power series. And it says, suppose that two power series, sum n equals 0 to infinity c sub n x sub n, and sum n equals 0 to infinity d sub n x sub n, converge to the functions f and g respectively on some common interval I. The power series sum n equals 0 to infinity c sub n x to the n plus or minus d sub n x to the n converges to f plus or minus g on that interval I. So that gives us a way of adding or subtracting two convergent power series, provided that we're on their common interval of convergence. So there's an overlap of where they converge. Second property, for any integer m greater than or equal to 0 and any real number b, the power series sum n equals 0 to infinity of bx to the m, so the bx to the m, that's just a constant, times c sub n x to the n is going to converge to bx to the m f of x on the interval I. And in the third property here it says, for any integer m greater than or equal to 0 and any real number b, the series sum n equals 0 to infinity c sub n bx to the m, and then that bx to the m all raised to the nth power converges to f of bx to the m for all x such that bx to the m is in I. That's where the series is going to converge. Okay, so let's do a couple examples. Look at an example of adding two power series, and maybe we'll illustrate those other two properties too. And so let's go and take a look here. Alright, so we're going to find the interval of convergence of this power series c sub x is equal to the sum n equals 0 to infinity 2n plus 1 over 2n plus 2, and then times x to the 2n. And we're going to use the ratio test. So it's going to be limit n goes to infinity of the absolute value of 2 times n plus 1 x to the 2 times the quantity n plus 1 all over 2 times n plus 1 plus 2. That's your a n plus 1 term. And then the a sub n is 2n plus 1 x to the 2n all over 2n plus 2. Okay, and then we'll keep flip and change and do a little bit of simplification. So we're going to have 2n plus 3 x to the 2n x squared all over 2n plus 4, and then we're going to flip the bottom fraction over. So 2n plus 2 divided by 2n plus 1 x to the 2n. We'll simplify that down some more. So this is the limit as n goes to infinity of 2n plus 3 times 2n plus 2 all over 2n plus 4 times 2n plus 1, and then times x squared in absolute value. The 2n plus 3 times 2n plus 2, that's going to be a degree 2 polynomial. And likewise on the denominator, 2n plus 4 times 2n plus 1 is going to be a degree 2 polynomial. Leading coefficients of both of them is going to be 4n squared, and so 4 over 4 will be 1. And so that limit is simply going to be x squared. And we want to know, for the ratio test, when is this less than 1? And that's going to occur when x is between negative 1 and 1. Okay, and that's your interval of convergence is negative 1 to 1. If you try the endpoints, the endpoints, either minus 1 or positive 1, you will be looking at an nth term, either this if it's 1, or, well, actually it's going to be that either case, because both negative 1 to the 2n and 1 to the 2n are both going to be 1. And so if we apply the nth term test, this goes to 1, which is not 0, and so that would say it diverges at the endpoints. And if we wanted to, we could also say the radius of convergence is 1. Okay, so that's our power series c sub x. We're going to look at a power series s of x. So s of x is going to be equal to the sum n equals 0 to infinity of 2n plus 2 over 2n plus 3 x to the 2n plus 1, and we're going to apply the ratio test on this one. So 2n plus 2 plus, 2 times the quantity n plus 1 plus 2 times x to the 2n plus 1 plus 1 divided by 2n plus 1 plus 3. Okay, and then the a sub n, which is 2n plus 2 over 2n plus 3 times x to the 2n plus 1. Alright, now we're going to simplify the numerator fraction a little bit. So it's going to be 2n plus 4 x to the 2n plus 3 divided by 2n plus 5, and we're going to flip the dividing fraction. So it's going to be 2n plus 3 over 2n plus 2 x to the 2n plus 1. And we're going to simplify this down some more. So that's going to give us 2n plus 4, 2n plus 3, x squared over 2n plus 5, and 2n plus 2. Now the reasoning for our limit and our interval of convergence is going to be pretty much the same as the previous, the c sub x power series. You're going to have a degree 2 over degree 2 of those polynomials. It's going to give us a 4n squared over 4n squared, so the limit of that is just going to be 1x squared. So when is that less than 1? That's when x is between -1 and 1. And so our interval of convergence is going to be -1 to 1, and your radius will also be 1. You can check the endpoints. It's not going to converge at the endpoints. Very similar argument to why the other series didn't converge. Okay. So why we were looking at this is we're going to now take these two power series, the c sub x and the s of x, and we're going to add them together. But we kind of got to get an idea of what they look like and also what's the common interval of convergence, and it happens to be the same for both of these. So given the c sub x, which was equal to the sum n equals 0 to infinity, and that was 2n plus 1 over 2n plus 2 x to the 2n, and s of x, which is equal to the sum n equals 0 to infinity, 2n plus 2 over 2n plus 3 x to the 2n plus 1. And what we're going to do is we're going to find the sum of these two series. And how we do that is we add up the like powers. So the coefficients on the x squareds you'd add, the x cubed, etc. So we're going to write out some terms to kind of see what this looks like. So c sub x, okay, when n is equal to 0, we're going to have 1/2 x to the 0 power, so it's just going to be 1/2. And then when n is equal to 1, it's going to be 3 over 4 x squared. N is equal to 2, 5 over 6 x to the 4th. N is equal to 3, 7 over 8 x to the 6th plus, what did we do? 0, 1, 2, 3. Here's n is equal to 4, 9 over 10 x to the 8th plus n is equal to 5, 11 over 12 x to the 10th plus, etc. So that's what the first 6 terms of c sub x looks like. Let's go ahead and look at what the first 5 or 6 terms of s of x looks like. So when n is equal to 1, we're going to have 2/3 and then x to the first power. So that's when n is equal to 0. So 2/3 x, n is equal to 1. We're going to have 4 over 5 x to the 3rd power. Okay. N is equal to 2, so we have 6 over 7 x to the 5th. Okay, so 0, 1, 2, 3. N is equal to 3, 8 over 9 x to the 7th plus n is equal to 4. 10 over 11 x to the 9th plus n is equal to, let's see, 0, 1, 2, 3, 4. N is equal to 5. 12 over 13 x to the 11th, and that keeps going on. Okay, so when we look at the c sub x and the s of x written out, notice that they do not have any powers that are the same on the x. So if we wanted to, this would be 0 plus 2/3 x plus 0x squared plus 4/5 x cubed plus 0x to the fourth, etc. So we're going to still add the coefficients on the like powers here. It's just they're going to be 0. Let's see how we want to say it. All the c sub x has all the even powers, s of x has all the odd powers. So we have a 0 to x there and a 0x cubed there, and so we're missing all of those. So c sub x plus s of x, what it's going to look like is 1/2 plus 2/3 x plus 3/4 x squared plus 4/5 x cubed plus 5/6 x to the fourth plus 6/7 x to the fifth plus 7/8 x to the sixth, and etc. 8/9 x to the seventh. And that's going to be equal to the sum n equals 0 to infinity. And we want to start at a 0, and so n plus 1 over n plus 2 is going to do that. We just want the denominator to be 1 more than the numerator, and we want the numerator to start at 1 and then just add 1 each time. So we go 1, 2, 3, 4, 5, etc. And we want the denominator to start at 2. So 2, 3, 4, 5, 6, etc. Okay, and then just regular old x to the first power. Okay, regular x to the nth power. Pardon me. Okay. All right, and so that's what that power series looks like, and then the interval of convergence is going to be where these two individual series overlapped in terms of the interval of convergence, which is -1 to 1. And so our radius is 1. Okay, I think we're going to look at one more example in this video. And we're going to use partial fractions to find the power series for the function f of x is equal to 10x plus 10x squared plus 187 all over x squared plus 4 and x squared plus 25. Okay. So when we perform our partial fraction decomposition, so 10x squared plus 187 over x squared plus 4 and x squared plus 25, okay, is going to be equal to, so we need the numerator to be 1 degree less than the denominator, so this is going to be ax plus b, so that's a first power over the denominator of x squared plus 4, and similarly for the second fraction, cx plus d over x squared plus 25. We'll go ahead and clear the fractions by multiplying by the common denominator of x squared plus 4 and x squared plus 25. So you have 10x squared plus 187 is equal to ax plus b times x squared plus 25. So ax times x squared is ax cubed. Ax times 25 is 25ax. B times x squared is bx squared, and b times 25 would be 25b. Likewise, we'll do the same thing, x squared plus 4 times the cx plus d. So cx times x squared would be cx cubed. Cx times 4 would be 4cx. D times x squared is dx squared, and d times 4 would be 4d. Okay, now we're going to group up the coefficients on the like powers. So we have the a and the c are with the x cubed. There's no x cubed on the other side, so it's a 0 coefficient on the left. So we have 0 is equal to a plus c. Now let's group the quadratics. So we got the 10, the b, and the d. So 10 is equal to b plus d. The linear coefficients we'll now do is 25, 4, 25x, 25a and 4c, and there is no linear coefficient on the left other than 0. And then the constant 187 is equal to 25b plus 4d. Okay, so let's see what we got going on. The first equation we can solve for a. A is equal to negative c, and we can substitute that into the third equation for the a. And so we have 0 is equal to 25 negative c plus 4c. And so that would tell us that c is equal to 0. And so if c is equal to 0, then so will a. All right, now let's go ahead and take the 10 equals b plus d. And we're going to solve by elimination method with the 178 equals 25b plus 4d. The easiest thing to do is to eliminate the d. So we're going to multiply the second equation by negative 4. So it's going to give us negative 40 is equal to negative 4b minus 4d. And then the second equation, 187, is equal to 25b plus 4d. So 147 is equal to 21b. Dividing by 21, b is equal to 7. So then 10 is equal to b, which is 7 plus d. So yeah, that should be a d here. Hold on a second. Not c. C we already figured out was 0, so this should have been d. Okay. All right, so d is equal to 3. All right, so our function f of x, now doing our partial fraction decomposition, is going to be 7 over x squared plus 4 plus 3 over x squared plus 25. And so we're out of real estate on this slide, so we're going to go ahead and hop over to the next slide to keep going with this. So we're just going to go ahead and rewrite our function here. 7 over x squared plus 4 plus 3 over x squared plus 25. And then we're going to go ahead and use the fact that the sum n equals 0 to infinity of ar to the n, that's our geometric series, that is going to converge to a over 1 minus r, and that is provided that the common ratio in absolute value is less than 1. So that's going to help us figure out what our interval of convergence is for this power series. Okay. So we need to manipulate 7 over x squared plus 4. We need to manipulate it to look like a over 1 minus r. So the first thing we're going to do is we're going to write it as 7 over 4 minus negative x squared. So we haven't changed anything. And likewise, we'll do the same thing with the other fraction. That'll be 3 over 25 minus negative x squared. Now it needs to look like a over 1 minus r. So we have the minus r part correct. Now we need the 1 minus r. So we're going to divide each of those respective fractions by 4 over 4 and 25 over 25. So it's going to be 7 over 4. 4 over 4 is 1 minus negative x squared over 4, or we could write that as negative and then x over 2 squared. And we'll do a similar thing, divide by 25, so 3 over 25, 25 over 25 is 1, and then minus negative x over 5, and just the x over 5 squared. Okay, and now we're ready to use the geometric series formula down below. I'm going to go ahead, and before I do that, I'm going to list my intervals of convergence. So we're going to take the common ratio, negative and then x over 2 squared, just the x over 2 squared. So that's going to tell us that negative 1 is less than x squared over 4, which is less than 1. So negative 4 is less than x squared, which is less than 4. Okay, and so that is going to tell us that x squared is going to be between negative 2 and 2. Okay. And similarly, a negative x over 5 squared in absolute value will tell us that a negative 1 is less than x squared over 25, less than 1. So negative 25 is less than x squared, which is less than 25. So the x will need to be between negative 5 and 5. Now the one that is more restrictive here is the minus 2 to 2. So in order to have convergence, the x will need to be between negative 2 and 2. Alright, so now let's go ahead and start writing this out. So the first series will be the sum n equals 0 to infinity of a, which is 7 over 4, and then our common ratio, which is negative and then x squared over 4 to the n power, plus the sum n equals 0 to infinity of 3 over 25, negative x squared over 25, and that's going to be raised to the nth power. So this becomes the sum n equals 0 to infinity of 7 times negative 1 to the n. So we're going to take this negative 1 out to the nth power over 4 to the n plus 1. So it's going to get an n here and a 1 there, so that becomes n plus 1. And then x squared to the n will be x to the 2n. Okay. Plus the sum n equals 0 to infinity of 3. And then here's our negative 1 to the n. 25 to the first, and then to the n, so that 25 to the n plus 1. X to the second power raised to the nth power would be x to the 2n. Okay, so we got matching exponents there, so we can go ahead and add up the coefficients, or subtract, in this case we're adding, so n equals 0 to infinity, of negative 1 to the n, so they had a negative 1 in common, 7 over 4 to the n plus 1, plus 3 over 25 to the n plus 1, and then that has x to the 2n. And so that is our power series for that particular function, centered at 0, and we're also able to find the interval of convergence. Alright, so that finishes up this video, so we'll see you next time, and I think there's going to be two more videos for 6.2.